Hello dear students, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss very important reactions, and these reactions maybe generally falls in the three different categories, and the students sometimes have the confusion about which one reaction actually gave the which kind of the product, and these reactions all are basically the Wurtz reaction. So today we will see the comparison between the Wurtz reaction and then Fittig reaction, that means Wurtz reaction versus Fittig reaction, and after that versus Wurtz-Fittig reaction. So I'll discuss all of these three reactions in the pretty much detail, but I'll give more focus to the Wurtz reaction as it is much more important for the examination point of view. However, this Fittig reaction and Wurtz-Fittig reactions are also important for the examination. So first of all, you should know how we can differentiate among the three different kinds of the reaction. So first of all, if you are observing any Wurtz reaction, so in the Wurtz reaction what we generally do, we will take the alkyl halide, and that alkyl halide in presence of the dry ether will along with the sodium will undergo the reaction, and you will get your alkane, or you say the alkane which have the more number of the carbon atoms as the byproduct. And what I missed here, the side product, and the side product would be in that case your 2Na+X. Okay, so this is just the example of the Wurtz reaction where I have taken this generalized reaction. Okay, and I'll discuss this reaction in pretty much detail as well. Now second is the Fittig reaction. So what is the difference between the Wurtz reaction and the Fittig reaction? So with Wurtz reaction, though the condition of the Fittig reaction is exactly equal to the Wurtz reaction, but these two will give you the different products. So in your Wurtz reaction, you are actually combining the two alkyl halides to give the alkane which have the higher number of the carbon atoms. But in the Fittig reaction, what we will do, in the Fittig reaction, we actually combine the two of the aryl halide, right? Benzene and over benzene you have the substitution of any halogen like bromine and chlorine or iodine, etc. And these two, when undergo the reaction under Wurtz condition, that is in presence of the sodium and the dry ether, then two of the benzene ring would couple, and they will give you the biphenyl of the product. And this is the biphenyl, but not the fused ring type of the system. You will get the biphenyl, but not the fused ring system. Okay, and again you can see here byproduct is the 2 of the sodium. So now this is quite clear. In the Wurtz reaction you will take the alkyl halide, and in the Fittig reaction you will take the alkyl halide, right? And the product would be different. In that case you will have the alkane which have the higher number of the carbon atoms, and in the second case, in the Fittig reaction, you will have the coupling reaction where the two phenyl group will couple to give you the biphenyl type of the compound, right? And the reaction condition is same for both. Third reaction is your Wurtz-Fittig reaction. That means you will combine the features of the Wurtz reaction as well as the Fittig reaction, and then the resulting reaction will be known as your Wurtz-Fittig reaction. So in that case, what we will do, we will take one of the aryl halide, say one of the aryl halide from the Fittig reaction, and one of the alkyl halide from the say Wurtz reaction. So we will now do the reaction between the alkyl halide and the aryl halide under the same condition, sodium and ether. Of course, we will take the ether again, and remember this ether is the dry ether. Okay, so what you will do in that case, your aryl halide will lose your halogen atom, and in place of this halogen atom, the substitution of your alkyl group will take place. So you will produce alkyl benzene in that case. Your product would be in that case alkyl benzene, right? So here you will get the alkyl benzene kind of the product, right? And in that case you will get the coupled product, and here you will get the alkane. So this is very important for you to differentiate among these three different kinds of the reaction. And one very important thing here, why we are using the DE in that case. DE means dry ether. Okay, so what is dry ether? Dry ether means ether without the traces of the water. You know, in this reaction we are using the sodium, and we want to react this sodium with the alkyl halide or the allyl halide, right? But not to the but not to the solvent. So generally, if you take, say, if you take the in place of the dry ether, if you take the water, then you know water and sodium will quickly react and your hydrogen gas will be removed, and the reaction will not occur on the alkyl halide on the aryl halide, right? But in case of the dry ether, you know, it's a dry ether is your non-polar solvent. Please remember, it's a non-polar solvent and do not react with the sodium at all, right? So basically what will happen in that case, this dry ether will coordinate this sodium, but it will not react with this one. Please remember, okay? But if you take the in place of the dry ether, if you take the wet ether, so wet ether will also have the water. So we cannot take the protic solvent or the polar protic solvent in case of the Wurtz reaction or the Fittig reaction or the Wurtz-Fittig reaction. We'll take the dry ether because we want to react our sodium with the alkyl or the aryl halide, but not to the solvent, right? That's why we are taking this dry ether. And sometimes in place of the dry ether, you can take the acetone as well, right? So this is how you can differentiate among these three different kinds of the reactions. Now we will discuss this Wurtz reaction in the pretty much detail. Okay, so guys, you must have noticed that in this particular example I have taken ethyl iodide, right? As you know, this iodide, this I is actually very good leaving group. In my lectures of SN1 and SN2 reactions, where I have explained the reactivity of SN1 and SN2 reaction, I have explained that whenever you take the alkyl halide, you better to start reaction with the iodide because it is a better leaving group. In the Wurtz reaction too, it would be better if you start your reaction with the alkyl iodide, right? If you don't have the alkyl iodide, then you can go with the alkyl bromide. These two are the best substrate for the Wurtz reaction as well. And after that, rarely you can take your alkyl chloride, and you will never take your alkyl fluoride, right? This will not do this reaction because fluorine and carbon bond is very strong. Moreover, fluorine is not a very good leaving group. That's why I have started reaction with this one, right? And one very important point you should also note that this primary alkyl halide, if you take the primary alkyl halide, this gives very good reaction, very good Wurtz reactions, followed by the secondary alkyl halide, while 3-degree alkyl halides actually are not good substrates for the Wurtz reaction, as they undergo the elimination reaction, your alkene would form in that case. So the general idea of the Wurtz reaction is that you will take sodium metal along with the two similar kind of the alkyl halide, and then you will couple with these alkyl groups of the alkyl halides, and you will end up with the alkane, right? This is the general idea, but the important thing is the mechanism of the reaction, how the mechanism of this reaction goes. So I'm going to explain the mechanism, and I'm explaining that type of the mechanism which is most widely accepted, right? You can clearly see the various steps. So step number 1 in this reaction is nothing but it is the formation of the alkyl radical. Step number 1 is formation of alkyl radical. Okay, this should be your small r. Okay, so how we can form this radical? It is quite easy here. First of all, say you have taken this R or X. Say I'm explaining the mechanism in the general way. Okay, if you want, then you can take the real example by taking the example of the ethyl iodide and say other type of the substrate, but I am generalizing it. Okay, and then you know you are having your sodium metal, and so you know what are the metals? Metals are electropositive. That means they have the tendency to donate the electron. So what this sodium will do in this particular reaction, it will donate its one of the electron to X, and this bond will undergo the cleavage. So one electron will shift onto the alkyl group, carbon of the alkyl group, and another electron will shift onto the halogen atom. Okay, and in this way you will produce this alkyl radical along with this NaX, where sodium is positive, X is negative, right? So this is your alkyl radical. This is the step number 1. And the step number 2 in this reaction is formation of alkyl anion. Step number 2 is formation of alkyl anion. This is the step number 2. So you have, in the first step, you have produced this alkyl radical. Now what will happen? The sodium metal, another sodium metal which is present, see, you will take the little of the sodium metal in which the lots of your sodium atoms would be there. So that sodium again will transfer electron to this alkyl radical, and when this electron transfer occurs, you will produce this alkyl anion, that is R negative, okay, and along with the sodium here, Na positive. So here clearly you can see this R, which is the alkyl part, negatively charged carbon is there, and you know whenever the carbon is having the negative charge, that means it is a nucleophilic carbon. So you will remember this point. Your carbon in the alkyl anion is nucleophilic in nature, okay, and once you know that it is nucleophilic in nature, and you already know that your alkyl halide undergoes the nucleophilic substitution reaction, right? So what will happen in the third step, right? Third step is quite easy. Here you see SN2 attack will occur. SN2 type of the reaction will occur. So I am writing SN2 attack on another alkyl halide molecule. Another alkyl halide, that is RX molecule, to produce the desired product. Okay, so here you can see you are having this R negative and Na positive, and then you are having the RX here, and the SN2 reaction will occur in that case. How the SN2 reaction will occur? So this nucleophile will attack onto this carbon, okay, right, and then this leaving group will be knocked out from here, and then you will end up with this species R, formed bond with that R, and plus you will have your NaX, and this is your desired product. So this is how the mechanism goes. Very, very important to understand the mechanism. See, if you are a beginner in the organic chemistry, you are in class 11th and you have just started to learn the organic chemistry, then these little things, if you remember, if you keep these things on your fingertips, then it will definitely enhance your reaction mechanism skill. Okay, so this is the general idea of the Wurtz reaction. So now when we have discussed the mechanism of the reaction, then what we can do, we can also discuss the limitations of the reactions, right? What are the limitations for these reactions? Okay, so limitations. First of all, you see, since this is a coupling reaction, you cannot produce methane in that case. So if you go back, right, in the previous slide, if you go back, then you can clearly see the two alkyl groups, basically they are coupling together to produce the increased length of the carbon chain in the alkyl group. In the previous slide, we have the real example as well, which is this butane, right? So since you are coupling the two species, then it is impossible to produce the methane with the help of the Wurtz reaction. This is something very, very important which you should know, right? And you see the second important point, you will only produce the alkanes which have the even number of the carbon atoms, right? So if you want to produce that alkane which have the odd number of the carbon atom, this will ruin the reaction, because it will give you the mixture of the product, and these mixtures are very difficult to separate. Okay, so I am writing here the second limitations for this. Only alkanes only alkanes with even number of carbon atoms. With even number of carbon atoms can be synthesized efficiently, can be synthesized efficiently, right? Say if you take the different kinds of the alkyl halide, right? It says, for example, you are taking this. Say first of all you are taking this CH3 CH2 I type of the compound, and you are reacting with this 2 of the sodium, and then you are taking CH3 CH2 CH2I. Okay, so in that case, of course, you will couple this species with that species. Okay, but you will end up with the mixture of the product. When you have the mixtures of the product, then desired yield would be low, and these mixtures actually requires too much of the techniques and money to separate, right? So third important limitation of this reaction is that you will always have the alkene as the side product, right? You will always have the alkene as the side product. Okay, so no matter whether you are using the similar kinds of the alkyl halides or the different kinds of the alkyl halides, one important problem with this reaction is that alkene is generally your side product. So how we can produce this alkene? Say for example, you have taken this RCH2 CH2 and negative. This anion, say I have produced, which I have produced in the previous slide as well, R negative Na. So I am not writing Na here. So say you have produced this, and say the SN2 attack is taking place. Say this is R, this is carbon and hydrogen, this is another hydrogen, and again your CH2, and say your Br, or not Br, say X I am taking. So what can happen in that case? You can see this your nucleophile can attack to this hydrogen, right? This is always possible, right? And when this is possible, so what will happen? This electron will be pushed here, and this halogen will be knocked out as it is your leaving group. Okay, so what will happen? R CH2 CH3. How I have produced this CH3? This negative charge grabbed the hydrogen from here, so this will become this, and this bond will be pushed back here. So when it will be pushed back here, so you will produce, or you will have RCH double bond CH2, right? So the formation of this alkene is another very important problem associated with the with this particular reaction. Next point, if you want, then you can remember tertiary alkyl halide, right? 3-degree alkyl halide does not undergo Wurtz reaction, as they undergoes the elimination reaction to produce the predominantly alkene, right? Predominantly alkene, as well as in that case also, if this alkyl group is quite bulky here, right? If you increase the bulk on the halogen side of this alkyl group, then again this alkene which is forming here, this would be the major product, and this is the minor product, right? So this is the general idea of the Wurtz reaction, but some very important examples which are very, very important for the NEET or the JEE examinations. Let's discuss all of them, or not all of them, few of them, because it is impossible for us to discuss each and every example, but I am giving you the little idea. For example, I am discussing intramolecular Wurtz reaction. So intramolecular coupling, or intramolecular Wurtz coupling, you can say. Intramolecular Wurtz reaction, you can say. For example, okay, say you are having this, this is your cyclobutane, right? See, Br is here, okay, and then your Cl is here. You can react with this 2 of the sodium metal, okay, and the reaction goes with the dry ether. Please remember, so I am writing De here for dry ether, and then you will have this particular product in that case, like that, right? You have produced this one. Of course, the geometry would not like that. Geometry is something like that in that case. but this is the way of explaining the things. Okay, here you can see this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, and this is the new bond which is forming between the two carbon atoms. Okay, so if you want to go for the mechanism, so what will happen, you, as you know, in that case, between this chlorine and the Br is the better leaving group, right? Since Br is the better leaving group, so what will happen in that case? Your sodium, okay, this will transfer one electron to this and this will shift here, okay, and when this happens, then you will produce this radical, Cl is over there and one electron is there along with your NaBr minus NaBr. So this radical you have produced, and in the second step what will happen? Sodium is there, this will transfer electron to this one, this will come here, and then you will have this radical. Okay, again NaCl would be removed from here, and then radical will combine, recombination of the radical will take place, and when the recombination of the radical take place, so I am writing combination or combining radicals, combining radicals. So they will combine in that case. So this is the example of the intramolecular coupling. So you may have the various examples like this. Okay, you may produce variety of the product with this reaction. Say for example, you are having this one. Let's say you are having 8-membered ring, right? Say this was your 1. Say this is your 2. 1, 2, 3, 4. This, and this. Suppose you are having this one, and what I am doing, I am numbering it. Say this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, and 8. So at the position number 8, I am putting my, say, leaving group I, and just at 4, I am putting my leaving group I. So what will happen in that case? If you take the 2 of the sodium, radical would be produced in that case, and that radical would be look like as follows, right? Say this was your 1, this was 2, this was 3, this was 4, 5, 6, 7, and 8. So radical we will produce from here, radical you will produce from here. Since you will knock out this I as the leaving group, this I as the leaving group, one electron at carbon number 4 and one electron at the carbon number 8, right? And then the radical recombination will occur, and when the radical recombination will occur, so they will be fused. Now in the fusion you can see here 2 5-membered rings will produce 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So how you can draw the structure for this one? Very simple. You simply draw the 5-membered rings 2. Right, so this is the desired product in that case. Okay, similarly you may have the variety of the reaction, right? Various strained kind of the molecules you can generate. Say for example you are having say this is your 6-membered ring cyclohexane, and say this is Br here and this is Br here. Again if you do the reaction, 2 of the sodium you will take, so definitely 2 of the NaBr would be knocked out. Of course dry ether would be there, please remember. So what will happen? The 6-membered ring, there is no problem in that, and this radical, okay, and then this radical. So if you number the carbon atoms 1, 2, 3, 4, 5, 6, okay, and then you see the combination will occur between this and this, right? The combination will occur. So how we can draw this particular structure? It's quite simple here. The product would be like that: 6-membered ring, and you connect with this one, right? So this was your carbon 1, this is carbon 2, this is carbon 1, this is carbon 2, this is forming like that. If you want to know the clear geometry, how it look like, so it is quite simple here. It look like this. Okay, just like that. So I am giving you the number, or I am giving the number to this molecule 1, 2, 3, 4, 5, 6, 7, 8. So I have explained the stereochemistry or the conformations of such species in the pretty much detail in my earlier lectures. I am giving you the link in the description box. You can go through these examples as well. And sometimes you see, guys, cyclization is also possible. Number 4 is the cyclization. So I am writing, say, cyclization. Okay. So how I can write the cyclization reaction for this one? Say for example, you are having this 1, 2, 3, and say 4. Okay. Say here I is there, and say here is Br. Okay. This is the starting material. And say this is carbon number 1, this is carbon number 2, this is carbon 3, this is carbon 4, this is carbon 5, and this is carbon number 6. And you are subjecting this reaction with the Wurtz reaction in the presence of the diethyl ether along with the 2 of the sodium. So clearly you see here what will happen. The radical will be produced. Where the radical will be produced? At this end, radical will be produced, and at this end the radical will be produced. Okay, so let's draw the radical first. Okay, say for example minus NaI first and then minus NaBr, right? See, if you compare the leaving ability of these two, then iodine is a very good leaving group. So first your NaI will be knocked out from here, giving radical to this carbon number 1, and after that your NaBr will be removed by the combination of these two, and at the point number 6 you will have your radical, right? So this is how the reaction will go. 1, 2, 3, 4, 5, 6, right? So this is the radical and this is the radical. Okay, and you know this is carbon 1, this is 2, this is 3, this is 4, this is 5, this is 6, and then these two radicals will combine, and when they will combine, so you will end up with the 6-membered ring. So you are producing your cyclohexane as well. So guys, there are various kinds of the reaction which are possible in this Wurtz reaction, and one very important reaction, a very important example I want to discuss with you. Say for example, you have been given this, say you have been given C8H8. Okay, it is basically a cubane. So how we can draw the structure for this one? Say this is one, this is another one, right? And then we can connect them 1, 1, 1 and 1. You can number the carbon atoms if you want. See, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So C8, and then remaining of the hydrogens would be there. On each of the carbon atom there would be one hydrogen atom. So what we can do actually, we can remove this bond from here. Okay, and when I remove the bond from here, what I can do, I can substitute it with this Br. So this is basically the alkyl halide. Okay, and when you do the reaction with the 2 of the sodium, and of course your dry ether would be there. So what will happen? See, when this reaction will go, so you will produce the radical like that. So you will produce radical here, you will produce radical here, and when you remove this bromine from here, and when bromine from here, so at carbon number 7 and carbon number 8 you will produce the radical, and finally the radical recombination would occur, and you will end up with the cubane type of the compound, right? So these are the very important reactions. I hope this will give you the very clear idea about the Wurtz reaction. So in the pretty much detail I have explained this Wurtz reaction to you. Please remember, in the Wurtz reaction you will always take the two of the alkyl halides, preferably of the same kinds. If you take the different kinds of the alkyl halides, then you will get the mixture, and alkene formation is always a problem in that case. Please remember, methane we cannot synthesize with this one, right? So in Wurtz reaction we take the alkyl halide at all. So let's do some of the problems based on the Wurtz reaction. So this is your first example where you have taken this particular compound in which benzene ring is already there, and the three substitutions are also there with the alkyl group, and among these three alkyl groups, two of them further substituted with the halogen. So basically it's a alkyl halide, it's not a aryl halide. So first of all you have to make a choice between the Wurtz reaction or the Fittig reaction, whether you will apply the Fittig reaction concept here or the Wurtz reaction here. Since it is the alkyl halide, because the substitution is on the aliphatic carbon atom, so it is a Wurtz reaction. Please remember, it's a Wurtz reaction, okay? And if it is a Wurtz reaction, then what kind of the product you can observe from here? So it's quite simple here, you know, when I have this sodium, so sodium can actually donate electron to this one as well as donate to this one, right? This bond will undergo the cleavage, homolytic cleavage, right? And this bond as well undergo the homolytic cleavage, and you will produce the radical here. So what kind of the radical you will produce here actually? So I am writing this radical in a little different manner, right? Say you have produced this radical here, CH2 radical is there, and at this position again you are having the CH2 radical, right? And here is the substitution of the CH3, okay? And of course two of the NaCl will be removed from here. So now it is quite obvious that since it is a Wurtz reaction, so it would be a combination between the two. So this is the one radical which I have produced here. Similarly, the same, since it is the Wurtz reaction, so you will always do this reaction with the two of this starting material. Of course, two of this material would also be there, and two of the NaX, right, will be removed from here. Now it would be 4 now, right, because 2 chlorine in one molecule, so 2 2s are 4, it would be 4 now, okay? So let's correct it, say it is 4. Now to understand the thing, it is very, very important. I am drawing this radical, the second radical again here. So how I can draw this radical? CH2 radical, and again this CH2 radical, and at this position you are having this substitution. So it is quite simple here. This will couple here, right? Electron would be coupled there, and you will have your product. So what kind of the product you may have in that case? So this is one benzene ring, and this is your another benzene ring, and here you are having the substitution of the methyl group. Here also you are having the substitution of the methyl group, and now you can see here this is carbon number 1, this is carbon number 2, and this is again 1, this is 2. That means between two benzene rings there is a bridge of the 2 carbon atom, right? There will be a bridge of the 2 carbon atom. So let's make that particular bridge. So how we can draw this 1 and 2? Say this is 1, this is 2. Similarly, you can draw another bridge here. Say this is 1, this is 2. So this is one of the product, right? So, but if you think that that's it, we have done with the reaction, it's wrong actually. Another product may also be possible. Say it may also happen that these two reactions, which are these two radicals, biradicals, which are combining here to produce this particular radical, sometimes it may give you the different isomer as well, right? Say this is actually coming, both are coming towards you, or both are on the same plane. So it's a cis kind of the transfer isomer. But what will happen when you have, say, this kind of the orientation of the two reacting species? Say for example, this is your CH3, okay, and say this is your radical, and again this is your radical. But another radical, right, this may take the orientation like that. Say this is CH2 dot and this is CH2 dot, and when the molecule flips, this can go up. So this will always happen that this actually can flip like that. When it will flip like that, so this will come down and this will go up and this will also go up. So this is what I have drawn here. Now if you combine these radicals again together, so this will come here, this will come here, this will come and this will come, and then your product would be like that. The two rings connected with the 2 carbon bridge like that. Okay, one is having the methyl substitution here and another one is having the methyl substitution here. So this product and this product, both these two products are possible in that case, right? This is the very important and very interesting examples, right? So now moving to the next one. Now I have some of the examples here which you know what will happen. This sodium will donate electron to this and this sodium will donate electron to this, right? When they donate electron to this, so what will happen? They will produce radical at this end, right? So how they will produce the radical? Okay, so this will come here and this will go there. The one electron will come here and one will come here. So you will have this kind of the radical species. This is radical and this is radical. Okay, and plus 2 of the Na. Br you will remove. Again this is the Wurtz reaction because it is the aliphatic compound. Okay, alkyl halide type of the compound. And now you know this and this can combine. So when these two combine, what will happen? So I am removing this electron here from the electron here, and when these two combine, this will join. So this is your product. Formation of a new 3-membered ring in this compound, right? So this is very very important. With the help of the Wurtz reaction, we can do the cyclization as well. We can take the we can form the different small ring type of the compound with the help of the Wurtz reaction. Very important. Now it is very easy for you to draw the say product for this particular reaction. Again, sodium and the dry ether, Wurtz reaction would be there. When Wurtz reaction would be there, you know what will happen? 1 electron to this by sodium and 1 electron to this. This will come up, this will go down, this will come up, this will go down, and then it will produce a radical here, and that radical would be 1 electron here, another electron here, plus 1 of the NaBr plus 1 of the NaCl. But please remember, in that case this bromine is better leaving group than the Cl. This bond is the weaker one. So first radical you will produce from this end. Once you have produced the radical from this end, only then you will produce the radical from this chlorine part. Please remember. Okay, now it is very easy. 1 electron here, 1 electron here, and they will form a covalent bond. Covalent bond is nothing but it is a pair of electron. So they can combine actually. Okay, they can combine to give you such kind of the product, one bond and another double bond. So this is another compound which you may produce with the help of this particular reaction. So this is very interesting and see, very important one, how we can produce the different rings here actually. Okay, so this is something very very important. Now my third reaction, again you can see this is the sodium and the dry ether, example of the Wurtz reaction. And let us modify this particular reaction. What we can do, we can label this carbon as carbon 14. You know, the carbon 12, carbon 13 and carbon 14 is there. So I have labeled this carbon as the carbon 14. It is very important to understand the orientation in the product, right? Chemistry of the product in that case is very very important. Now since it's a Wurtz reaction, what can happen, right? 1 electron like that, one will come up and one will go there. Of course here NaCl would be removed. There is no problem in the removal of the NaCl. And guys, then you can look forward for the generation of the radical. So this is one radical which you have produced. What can happen? This radical again and can undergo the resonance. So this double bond will break, bond will come here and this will come here. Remember, this is the carbon number 14. Okay, and not carbon number, isotope of the carbon, which is labeled as the 14, right? So this is how now the double will go there, and this carbon 14 you will have this radical. So you are having this radical, you are having this radical. So what can happen in that case? First of all, I am drawing or I am writing the product for this one. Say this is your radical which you have produced and this is your 14. So two such radicals will combine. Okay, this is 14. Now you can see, guys, what we can do. This is the electron, right? So here you will produce a bond. Okay, and to make you understand a little more correctly, I am writing my labeling in a little clearer way. So this is 14 and this is 14, right? This is one of the product. I hope this is quite clear. Now this is quite clear. Now I can draw the product with this one as well. So when you draw this actually, so this is one, and you are having radical here at 14. Okay, and then again you will draw like that, radical at 14, and they can combine to form a bond. So there would be a bond between the two. So what is the difference between these two products? Here labeled carbon is this, which is 14 here. Here labeled carbon is the correcting carbon. So two products are possible in that case. This is 1 and this is 2. And another product which is also possible, since I need some space, so I am deleting some part. You can take the snapshot. Okay, I have removed this one. Now what we can do, we can combine these two radicals, right? Say you are having this species where this 14 is labeled, and then you are having this species where 14 carbon is itself a radical. Okay, and we can always combine these two, and so when we combine these two, what we will end up? We will end up with the formation of this kind of the product. Okay, double here, but this would be labeled as 14 and this is labeled as 14. So this product, and this product, that means 3 different kinds of the products are possible in that case. See how interesting this Wurtz reaction is. Now after this Wurtz reaction, let's see what is the Wurtz-Fittig reaction and how the mechanism of this reaction goes. So as I explained in the starting of the lecture, in case of the Fittig reaction, we will react 2 of the aryl halide of the similar kinds or the different kinds to get the say biphenyl type of the compound. That means the coupling will take place in that case. Please remember. Okay, so this is just for example, if say you are having this starting material 2 of the say iodobenzene, and you are reacting it with the sodium. Okay, and then you are having the dry ether here. Okay, ether dry or the dry ether you are having. So what will happen in that case? You will have the coupled product. Coupling would occur in that case, and you will have these biphenyl type of the compound. This is just the basic reaction, and your 2 of the sodium iodide would be removed from here. So this is the very important compound, and few years back, see, it was a very hectic and the tedious task for the scientists to generate such kind of the molecules. But now they actually succeed in the synthesis, in synthesizing this biphenyl type of the compound, right? But few years ago it was quite difficult. Okay, so here I have taken this particular example, and the condition is quite same in that case. So and I have taken either aryl iodide. Why aryl iodide? Because iodine is the very good leaving group, as I explained in case of the Wurtz reaction as well, right? So if you want, then you can take the different kinds of the starting material as well. Say for example, you are taking this one. Okay, this, and say you are taking I here, and then you are taking say Br here, and the condition is same in both the cases, sodium. So again you will get your coupled product like that. okay, and then you are having your NaI and then NaBr. So variety of the reaction you can do by your own, and if you want then you can substitute these positions with the different kinds of the prefixes to increase the reactivity of the particular alkyl halide to get the desired product with the particular kind of the substitution. You may practice by your own by taking the different examples, but I am not taking the different examples here, but I am telling you here in that case when you do the reaction. So first of all, this iodide, aryl iodide will undergo the reaction because this bond is the quite weaker one, okay, and and then you can see the, okay, what is the mechanism, how the mechanism is going how taking place in that case. So let's check the mechanism, how it happens actually. Say for example, you have taken this, right, this and this, and here your I is there, okay, and you know your sodium metal is there, which is electropositive, which will give the electron to this I, okay, and this bond will undergo the homolytic cleavage. One electron will go to the I and another electron will go to this particular position, okay, and then of course you have taken dry ether. I am writing De for the dry ether. So what you will do here, you will produce this kind of the radical along with your, say, NaI. So this is the first step, which is the production of the radical. Since you will start this reaction with these two, so you can balance this right, and then you can write these two like that. So two of the radicals are there, right, one radical, and then you are having another radical which you have produced, okay, and then these two will form a bond, and then you will have your biphenyl type of the compound, right. So this is how your fitting reaction goes. I hope you understood the things, but what you can do, you can take the different examples where you can change this leaving group, or you can substitute this, right, and you can observe that how the rate of the reaction will vary when you do the different kinds of the substitution over there. So this is the fitting reaction. I hope this is quite okay for you. Now I am going to discuss my last reaction in that case, which is the Wurtz-Fittig reaction, and the Wurtz-Fittig reaction is a little bit more typical in that case, right. So here I can write Wurtz-Fittig reactions. So what will happen in that case? Say for example, I am taking this. I am taking, say, this bromobenzene, okay, and I am reacting this bromobenzene, say, with your methyl iodide, right, and of course your sodium metal would be there along with your dry ether, because you are taking sodium which is electropositive, which will donate the electron to the alkyl or the aryl halide system. So you cannot take the polar solvent, as I am explaining throughout this particular lecture, okay. And now see, now it is your up to your basic knowledge of general organic chemistry. You know, when you have the aryl halide and you have the alkyl halide, and you want to check the reactivity of these two, so you know this alkyl halide is more reactive. Please remember, alkyl halide is more reactive, right, while this aryl halide is less reactive. See, what generally we do in this particular reaction, we either remove this Br or the I from here, right. So why this bromobenzene or your aryl halides are less reactive? So generalization is like that. Your aryl halides are less reactive than alkyl halides, and one obvious reason is that, say for example, you are having this, okay, and this Br is over there, you know, the three lone pairs are there, okay. So this will come here, this will go there, and resonance will take place in this particular molecule, or the mesomeric effect you can say. This would be double now, and you left with the two lone pairs only. This is positive over there, this is negative, this is negative, and then you can draw the various others resonance structure for this one. I am not drawing all the resonance structure. I have drawn only these two to explain the things. You know, this is now in the resonance structure, this is the double bond nature between the halogen and this particular carbon, and this double bond is quite stronger and shorter, so the breaking of this bond would be difficult in that case. While this kind of resonance is not possible in case of the alkyl halide, so this is more reactive than the your aryl halide. Please remember, this is general organic chemistry, you should know all these things. And initially I already told you, in this reaction we will do the alkylation of aryl halide. Alkylation of aryl halide means you will substitute this bromine with the CH3, and of course your byproduct would be there, like say NaI or your NaBr, both are there. But if you take the similar kind of these things, say you can take I here and I as well, so you will get your 2 of the NaI as the side product. So here you have produced the toluene, right? And this toluene is what? This toluene is what? This is alkyl benzene, right? So you can produce or you can synthesize variety of the alkene benzenes with the help of the Wurtz-Fittig reaction, in which you are taking the one substrate of the Wurtz reaction and other substrate of the Fittig reaction and combining these two to get the Wurtz-Fittig reaction. Then how the reaction mechanism goes? So let's talk about the mechanism. Okay, let's talk about the mechanism of this Wurtz-Fittig reaction. So I already told you, this alkyl halide is more reactive comparison to the aryl halide. So what will happen? This will react with the sodium. Okay, and when this will react with the sodium, you know what the sodium will do? This will donate one electron to this one. Okay, you will produce this NaI type of the compound, right? And say you have taken 2 here, right? So what will happen in that case? You will produce the NaI here plus, and then you will produce the CH3Na type of the compound. You know the electronegativity of carbon is much higher than the metal. So this is your positively charged, this is your negatively charged. So basically what you have done, you have produced here alkyl anion. What you have produced? Alkyl anion type of the compound you have produced. This is the step number 1. Okay, then what will happen? Second, what you have taken? You have taken, I think, Br in the previous slide. Okay, and then you are having this CH3 of Na. You know, this is positive, this is negative. Okay, and then here you can see the nucleophilic substitution will take place. So this will attack here and simultaneously this will move from here. Okay, so what will happen in that case? Your NaBr would be removed. Okay, and then you have the substituted product. This is your CH3, right? So this is how you can do the reaction. Okay, so this is the mechanism, very simple mechanism, right? And what you can do here, you can take the variety of the different kinds of the substrate and then you can react with them with each other. Say you may have the question in the examination, produce the ethyl benzene with the help of the Wurtz-Fittig reaction, then you can change the nature of the substrates. Now it is up to you whether you will change the nature of the alkyl halide or the aryl halide. This is your practice for your practice. So it's the very important application, alkylation of the aryl halides applications, right? First, you know, alkylation of aryl halides. Okay, and second very important application you can take synthesis of organosilicon compound. Organosilicon compounds with the help of the Wurtz-Fittig reaction. Say for example, you have taken this, silicon O C2H5 times 4, tetravalency of the silicon is there. Okay, here silicon alkoxide, you can name it. Okay, and then you can take the 2 of the sodium, right, and then you can take, say, your 3-degree alkyl halide, say Cl I am taking here. So in that case you will produce Si OC2H5 whole thrice OC, and then CH3 whole thrice. Of course here sodium chloride will be removed from here, and one more thing, C2H5ONA will also be removed. So this is a very important reaction, right? So you see what I have done here. I have taken one of the ethoxide, right, from here, and combined that ethoxide with the sodium to remove C2H5ONA, sodium ethoxide, and one of the sodium will react with this chlorine, right? So this will be removed from here, and finally there will be a linkage between this and that silicon part. So SiOC2H5 whole thrice, and then you see OC and CH3 whole thrice. So this is how you can do this kind of the reaction, right? Okay, I hope you enjoyed the lecture. If you understood the things, please like the lecture, do share with your friends as well, and don't forget to subscribe my channel Tetrahedron Chemistry Classes.